Hello, my name is Aaryan Chatterjee, and this is my Faraday's Law Lab 6 in Physics 2212. In life, some objects have magnetic flux, which is the flow of magnetic fields through a surface. This phenomenon is another wonderful interaction that can affect objects like creating currents. This lab will focus on analyzing how a changing magnetic flux, which Faraday tells us about, can affect falling time. More specifically, the purpose of this lab is to analyze a magnet falling through an aluminum tube using Faraday's law and flux and determine the amount of time the magnet spends falling through the tube. In this experiment, we will have an observational and computational model, which will both analyze how the magnet falls through the tube. Later, we will see that our models provide similar results, and the time the magnet spends falling in the tube is around 1.4 seconds. Before we jump straight into lab specifics, it is important to understand some of the crucial physics lab principles and ideas utilized in this lab. Firstly, it's important that everyone understands the Biot-Savart law, which models the magnetic field of a point using the equation shown on the slide, where it can be manipulated to find the magnetic field from a dipole. Additionally, Faraday's law tells us that a change in magnetic flux will create a voltage in a loop of the surface that it went through. Then Ohm's law tells us that V equals IR, and we can use Faraday's law and Ohm's law to find the current in the rings of the tube later in this lab. Then we also have Newton's second law, which states that net force equals mass times acceleration, and we have Newton's third law stating that every force will have equal but opposite force. Now we just cover some major assumptions in the experiment, and one is that there is no external factors that are affecting the bar magnet or the tube in the experiment. This means that air resistance is negligible, and the only forces on the bar magnet will be from the tube and gravity. On top of the assumptions, it's important to know that the system, which is what we will analyze, is a bar magnet and the aluminum tube in the experiment, and everything else is surroundings like the earth, table, and more. Now, for the experiment, we will hold up an aluminum tube and simply drop the magnet into it, and then we will record the time it takes for the magnet to come out of the tube. Now, moving on to the observational model, let's first define the initial conditions. So the magnet's mass is 0.025 kg, the tube's length is 0.46 meters, the tube width is 0.006 meters, and the magnet starts at rest and starts falling at t equals 0 seconds. Now that we got that out of the way, this is the lab experiment video. So as you can see, the magnet took a little bit longer falling inside the tube, so we know something's going on, which we'll explain more in the computational model. So after dropping the magnet 5 times, we got the average time to fall out of the tube was 1.396 seconds. Now let's move on to the computational model. So we first start off by defining constants and defining the initial conditions in the code, which is done in the left picture and the top right picture. Then we define a function to find the magnetic field of a falling magnet at some location using the Biot-Savart law, and then we also we create a function to find the change in flux from the magnet on a particular ring in the tube, and these two functions are in the bottom right picture. Now that we have defined our functions, we will then start a loop to calculate the flux of many rings in the tube as the magnet falls. For each ring in the tube, we calculate the change in flux which induces a voltage in the ring, which in turn creates a current that we can solve using Ohm's law. Now, since each ring has a current, they will provide a magnetic force in the bar magnet, which we will calculate and add the force onto the ring from the bar magnet to get the total magnetic force. Then we will calculate the net force on the magnet by adding the total magnetic force and the gravitational force. That allows us to finally use the velocity update formula and the position update formula to find out how fast the magnet is going and where it currently is. After that, we have fully analyzed the magnet's path through the tube and simply need to print out when the magnet exits the tube. Moving on to the computational results, on the left is an image of what the animation looked like at a certain point, with the magnet being in the middle of the two colored rings, and the two rings being colored differently indicates that the current is in opposite directions. But we will talk about that more on the next slide. Additionally, this velocity and time graph shows us that at first the gravitational force is stronger than the magnetic force at the start, but when the magnet gets inside of the tube, the forces equal each other, making the magnet move at a constant speed. Then again, the gravitational force is stronger once the bar magnet reaches the end of the tube. And finally, the computer also tells us that the time in the tube was 1.377 seconds, which is extremely close to the experimental results. Now let's answer these questions, starting with the first one. We know that the red loop is counterclockwise and the blue loop is clockwise due to Lenz's law. If the magnet were flipped, nothing would change in the experiment, except the currents in the rings would be flipped. Additionally, the computational and experimental results were very close, and the computational model could get more accurate if they considered air resistance. Finally, like I said before, the graph tells us that the gravitational force is stronger at the entrance and the exit of the tube, but the magnetic force and the gravitational force are equal on the inside of the tube. Although our lab provided pretty accurate measurements, there could have been some sorts of error. For instance, the magnet and the tube could have felt other fields from laptops, phones, and more things in the lab affecting our results. Additionally, the magnetic dipole moment used in the code could have been a bit off, and humans clicking the timer too fast or too slow could affect the results. For the what-if questions, if the resistivity of the conductor was reduced a lot, the current of the loops would increase, resulting in a stronger magnetic force on the magnet, resulting in a slower fall and a longer time. Additionally, if holes were cut into the tube, that would decrease the rings, reducing the number of currents, and thus the magnetic force on the bar magnet, resulting in a faster fall and shorter time. That's all from our presentation. Thank you for listening.